Compounds like CCl₂F₂ are known as chlorofluorocarbons or CFCs. The compounds were once used as refrigerants but now being replaced by other compounds which are less harmful to the environment because it has been known that CFCs destroy the ozone layer. The actual question starts from here. The heat of vaporization of CCl₂F₂ is 298 joules per gram. What mass of this substance must evaporate in order to freeze 100 grams of water initially at 18 degree? The heat of fusion of water is 334 joules per gram and specific heat of water is 4.18 joules per gram Kelvin. In order to understand how to solve questions based on energy of phase changes and heat involved in phase transfers, we need to first understand the heating curve and what it involves. A heating curve is the curve of temperature versus the amount of heat added at a constant rate as the substance changes phase or simply increases its temperature. Let's assume we start with a substance that's below its freezing temperature or freezing point. So the substance will start as a solid. As we add heat, the heat would be used to increase the temperature of the solid because adding heat will increase the kinetic energy and increasing kinetic energy increases temperature. The equation used to calculate the heat required to increase the temperature of a substance from an initial temperature to a final temperature is mc delta T. Q equals mc delta T, where delta T is the difference between the final and the initial temperature, m is the mass of the solid, and C is the specific heat of the solid substance. Once the solid has reached the melting point, it begins to melt. Further addition of heat is used not to increase the kinetic energy of the substance, so there's no change in temperature. Instead, the heat added is used to overcome the interparticle attractions and convert the solid into a liquid state. The energy needed to convert a solid into the liquid state or to carry out a phase change where there's no change in temperature is mass times delta H of fusion or latent heat of fusion in joules or kilojoules per gram. But if the latent heat of fusion is given in joules or kilojoules per mole, you'll need to multiply the moles with the latent heat. Once all the solid has turned to liquid, further addition of heat is used to increase the kinetic energy or motion of the liquid particles until they reach the boiling point. The equation needed to calculate the heat absorbed when a liquid changes its temperature from some initial point to a final temperature, as long as it stays the liquid, is mc delta T, where delta T is the difference between the final and the initial temperatures. C is the specific heat of the liquid, which will not be the same as specific heat of the solid. And m is the mass of the liquid. Now the liquid has reached the boiling point and further addition of heat will cause it to boil or vaporize. The equation needed to calculate the heat used to vaporize a liquid to the gas is mass times the enthalpy of vaporization or latent heat of vaporization if it's given in joules or kilojoules per gram, or times moles if it is per mole. So notice that again, this is a phase change and that happens at constant boiling point, so there is no change in temperature. Once all the liquid has turned to gas, further addition of heat will cause the temperature of the gas to increase. And since there's no phase change here, just a change in temperature because of increase in kinetic energy, the equation used to calculate the heat to change the temperature of a gas is mc delta T, where C is the specific heat of the gas, which will be different from that of a liquid or a solid even for the same substance. Delta T is the difference in temperature and m is the mass of the gas. So you'd notice that in the slopey portions where the substance is just increasing the temperature, whether in the solid, liquid, or gaseous state, the equation you need to calculate the heat change in any of these portions is mc delta T. Whereas in the flat horizontal portion, where two states are at equilibrium or they're involved in a phase change at constant temperature, either constant melting point or constant boiling point, you would use the latent heat of that phase change, fusion or the vaporization, times the mass or the moles. In this question, we have two substances. One is the chlorofluorocarbons present as refrigerant, and the other is water. Now we'll need to break this process of evaporation of water, 100 grams water initially at 18 degree, into some certain number of steps, because each step would require a different formula for calculation of the heat change involved. So first we have 100 grams of water that's initially at 18 degree. We'll first bring it down or cool it to the freezing point, that's 0 degree. Once it's at 0 degree liquid, you want to cool it further so that it freezes to solid state at the same temperature, the freezing point. The energy released when water is cooled from 18 degrees to 0 degree is Q equals mc delta T. We use this equation because there's no change in state, only a change in temperature. The equation to cool water from 0 degree liquid to freeze it to solid state 0 degree. Here, since there's no change in temperature, only a change in state, we have to use the latent heat for that state, which is fusion or freezing, opposite of melting. So let's state this is step 1 and this is step 2. So you have cooled water from 18 degree to 0 degree and then froze it to solid. Let's say Q1 is energy released in the first step and Q2 is energy released in the second step. The total energy released, Q, is Q1 plus Q2. M is the mass of water, 100 grams. C, specific heat of liquid water, 4.18 joules per gram Kelvin or degree Celsius. Delta T is a change in temperature. The change in temperature in degree is the same as the change in temperature in Kelvin. So conversion from Kelvin to degree or the other way around is not required. Plus mass of water is 100 grams times enthalpy of fusion is given here in the question as 334 joules per gram. This is 7524 joules and the energy needed to freeze it is 33400 joules, adding up to 40924 joules. This is the total energy that will be released by water. Now this heat energy released by the water is used to evaporate the CCl₂F₂. Water loses the heat to the CCl₃, which uses it to evaporate. The total heat absorbed by the CCl₂F₂ should be equal to the total heat lost by the water and the heat absorbed by CCl₂F₂ to evaporate is given by the mass of the CCl₂F₂ times the enthalpy of vaporization of CCl₂F₂, and that should equal the total heat lost by the water while cooling. That's 40924 joules. The mass of CCl₂F₂ would be 40924 divided by the enthalpy of vaporization of CCl₂F₂, which is given in the question as 298 joules per gram. which gives us 137.32 grams. So this is the mass of CCl₂F₂ that would evaporate in order to freeze 100 grams of liquid water initially at 18 degrees. Ethanol melts at minus 114 degrees Celsius and boils at 78 degrees. The enthalpy of fusion of ethanol is 5.02 kilojoules per mole, and its enthalpy of vaporization is 38.56 kilojoules per mole. Melting point of ethanol is negative 114 degrees, and the boiling point is 78 degrees Celsius. The question asks us to convert 75 grams of ethanol initially at minus 120 degrees Celsius. If you check where negative 120 degrees Celsius is on the graph, you'd find that it's below the melting point. So the entire process of converting ethanol from negative 120 degrees Celsius all the way to vapor phase at 78 involves several steps. Ethanol starts off as a solid at negative 120 degrees Celsius, and you would need to raise its temperature till it reaches the melting point of negative 114 degrees. The energy, let's say Q1, needed for this phase change is mc delta T. Next, we want to convert the solid to the liquid, and the energy needed for this is mass times enthalpy of fusion. Let's say the energy needed for that is Q2. Once all the solid has been turned to liquid, you need to raise the temperature of the liquid all the way to its boiling point. The energy needed for this, Q3, is mc delta T. Once it's all converted to liquid, you want to vaporize it because we want to convert it to a vapor phase at the boiling point. The energy needed for this, Q4, is mass times enthalpy of vaporization. So whenever there's a phase change, you'd use the latent heat of vaporization times the mass, or latent heat of fusion times the mass. And whenever there's a temperature change without a phase change, you would use mc delta T. So let's break this process into steps. So we have 75 grams of ethanol at negative 120 degrees Celsius in the solid, and you want to increase the temperature of 75 grams of ethanol to its melting point, negative 114 degrees Celsius, energy Q1 mc delta T. Next, you want to convert the solid into the liquid at its melting point. The energy needed for this, Q2, is mass times enthalpy of fusion. Notice that there's no change in temperature, only a change in phase. Once it's completely turned to the liquid, we need to raise the temperature of the liquid all the way to its boiling point. At 78 degrees. The energy needed for this, Q3, is mass times the specific heat of the liquid times delta T. And finally, you want to evaporate all the liquid to the gas at 78 degrees. There's no change in temperature, only a change in state, so the energy is mass times the latent heat of vaporization. Q1, the first energy, is mass of ethanol, 75 grams, times the specific heat of solid ethanol, which is 0.97 joules per gram Kelvin, times the temperature change of ethanol, which is the negative 114 minus of minus 120 degrees, 0.5 joules. Enthalpy Q2 is moles times delta H of fusion. Because enthalpy of fusion is given in kilojoules per mole as well as vaporization given in kilojoules per mole, I would multiply the moles with the joules per or kilojoules per mole. So for this, I'll need to find the moles of ethanol in 75 grams of ethanol. So that is the moles divided by the molar mass. The molar mass of ethanol is about 46.07 gram per mole, which you can calculate because this is ethanol's molecular formula. You have 2 carbons and a total of 6 hydrogens and 1 oxygen. Their masses adding up to 46.07. 1.63 moles. So it's 1.63 moles times the enthalpy of fusion, which is 5.02 kilojoules per mole, 8.173 kilojoules, which is 8173 joules. Next process, Q3, is increasing the temperature of the liquid from negative 114 to all the way to the boiling point 78 MC delta T, where M is the mass of ethanol. Specific heat of liquid ethanol is 2.3 joules per gram Kelvin, and change in temperature 78 minus of minus 114 degree. 33120 joules. The last step is the vaporization at the boiling points of 78 degrees. Again, no change in temperature, just a change in state. The moles of ethanol are the same, 1.63 moles times enthalpy of vaporization is here, 38.56 kilojoules per mole. (62.87 kilojoules or 62870 joules). The total heat is the sum of all the Q1 through Q3, through Q4, which is 104.6 kilojoules. The chlorofluorocarbon C₂Cl₃F₃ has a normal boiling point of 47.6 degrees. Specific heats of liquid and gas are 0.91 and 0.67 joules per gram Kelvin. The heat of vaporization of the compound is 27.49 kilojoules per mole. Here we start with 25 grams of the chlorofluorocarbon as a liquid at 5 degrees Celsius. I need to increase the temperature of the liquid all the way to its boiling point, which is 47.6 degrees Celsius, without a change in state. I have to use the heat formula, Q equals mc delta T. Next, I will convert this to a gas at constant boiling point. The heat required for this step, let's say it's step 2, so Q2, mass times latent heat of vaporization. Next, I need to raise the temperature of this gas all the way to 82 degrees Celsius, which is the last step. And since there is no phase change, just an increase in temperature of the gas. The step 3, Q3, is mass times specific heat of the gas times change in temperature of the gas. This is the given data. For step 1, Q mc delta T, I've used the mass of the liquid times the specific heat of the liquid, which is 0.91, And then change in temperature is a final temperature of 47.6 minus initial 5. The heat required is 967 joules. In the second step, since I'm given the molar enthalpy of vaporization in kilojoules per mole, I'll need to convert the 25 grams of my chlorofluorocarbon to moles. So 25 divided by, this is the molar mass of the C₂Cl₃F₃, if I add up all these masses. So I get this moles, and then Q2 will be moles times enthalpy of vaporization. So that's 0.133 moles times kilojoules per mole. And so I get Q2 in kilojoules. I can convert it to joules because I'll need to finally add up all the Qs in the same unit. The third step, MC delta T, but I use the specific heat for the gas, which is 0.67 joules per gram per Kelvin, and from a final temperature of 82 minus the initial 47.6. And Q3, this is what I get, and the total heat, I add them all up in joules and divided by 1000. This is the answer in kilojoules.